Thank you very much for the introduction. And thank you to all the organizers for making a great conference and for inviting me. I'm currently a postdoc in the group of Basil Crucial in Bristol. And besides playing badminton, sometimes we do theoretical photochemistry. So we're interested in what happens when a molecule absorbs a light. And so this is a schematic picture of how we think about it. We have a molecule in the ground state, photon comes in, excites it to some excited state, and induces some kind of dynamics, which potentially leads to photochemical reaction and produces some products. I will not focus on the dynamical part today that much. And the group kind of does method development, coding, and also applications. So I am more on the application and coding side. And in particular, we have project on studying molecules in the atmosphere. So it turns out that atmosphere is not just oxygen and nitrogen. There are a lot of organic compounds which are collectively called volatile organic compounds. They can come from biogenic sources, so from plants, for example, but of course they also come from us, from anthropogenic pollution. And we would like to understand the fate of these molecules, because it's very important to be able to model and to, for example, predict if we suddenly start introducing a lot of molecules in the atmosphere, what happens to them if they create some kind of pollution and so on. And so atmospheric chemists spend a lot of time creating these huge kinetic databases of networks of hundreds of reactions. And they can model these things quite accurately. But one thing that they are missing for a large part is photochemistry. So most of these kinetic mechanisms are ground state based. And the reason why photochemistry is a bit hard is because we're missing the experimental data. So to get a photolysis rate constant, which is a rate that the molecule will react with photon, we need three things. So we need an actinic flux, which is just the number of photons that we have, either in the experiment or in the atmosphere. It's given by the solar flux. We need a quantum yield, which is just the probability that when a molecule absorbs a photon, that it will do something instead of just going back to the ground state as it was. And then we need absorption cross-section. So that's the probability that the molecule will actually absorb the photon. And so when we multiply these together and integrate over the wavelength, sorry, I'm missing the integration sign, so we are integrating over wavelengths of light, we can get the photolysis rate constant. And so photoabsorption cross-section and quantum yield can be measured, but it's very hard. Even just the absorption cross-section for gas phase molecule is hard to measure, especially for molecules which are reactive intermediates and which you can't actually isolate and manipulate in lab. So we would like to predict this theoretically. And so I will focus on the absorption cross-section part. And just to get us on the same page, we are talking about UV-vis spectroscopy, UV-vis absorption. So we are electronically exciting the molecule. So you can just imagine simply we are promoting an electron from one orbital to another orbital. So in this case, we are exciting an electron from non-bonded oxygen orbitals into antibonding orbitals. So that's just an example. And we can calculate things that we need for absorption cross-section from quantum chemistry. For example, from TDDFT, what we need is excitation energies and transition dipole moments, which gives us the probability of excitation. So we need these two things. And so naively, if we just did this for a single molecular geometry, we would get a thick spectrum like this. So it would, instead of getting the whole spectrum, we would just have a single transition. But of course, we know that the molecules are not frozen in place, they vibrate. And so we somehow need to include the coupling of the electronic and nuclear motion. And one way to do that is an approach called Frank-Condon, where we need to calculate the excited state vibration levels, and then we can calculate the so-called Frank-Condon factors. And summing that all up will give us the whole spectrum, including the vibrational resolution. So these little peaks is the vibrational resolution in the UV spectrum. That works and can be done. It's if your molecule is large enough, it gets quite difficult. But it also has other problems, because one of the things is that this is a very simple picture, but in reality, it may look like this. So you have many, many excited states that are crossing. Some of them are not even bound, and they are dissociative. So you can't really calculate like vibration levels. And so what do we do in this case? And with apologies to all the speakers from yesterday who were talking about ultra high precision spectroscopy, I'm just going to close my eyes and pretend that the vibration levels in the excited state are not there. We're just going to, just bear with me. But we'll keep one eye open, because we still need to get the ground state distribution, this one. And when we do have the ground state distribution, we will sample it. So we will randomly choose geometries from this distribution. And for each of this geometry, we'll calculate the excitation energies and transition dipole moment. And then we essentially do a histogram. And that's our spectrum. That's incredibly naive. And of course, we will not get vibration resolution, but we kind of get the overall shape of the spectrum. And we don't actually really care about the fine structure of the spectrum, because as we saw previously, we only care about the integral over the spectrum to get the photolysis very constant. So this approach, although it might seem incredibly naive, actually works reasonably well. And we've been testing that on many organic molecules. But also it has some advantages over kind of the naive Frank-Condon approach, because it can be, well, it's computationally cheap. It can be applicable to large systems. It handles dissociative state really well, which you can't really easily do otherwise. You can include solvation effects. And one thing that's quite important for our case is that it includes non-Condon effects very easily. So non-Condon effect is the dependence of the transition dipole moments on the molecular geometry. And so sometimes for certain kinds of molecules, the reflection principle approach actually provides a better spectrum than you would get by naively doing the Frank-Condon one. So this is the idea. And now we would like to somehow make this method accessible to people who are perhaps not experts in the field. And so we would essentially want to create the workflow that you can just run yourself. And so the workflow looks like this. You need to provide a molecular geometry. Ideally, you don't actually need to build a molecule. You can just provide a SMILES code, which is just a string that describes the molecule. And then it will generate the molecule. You can do some kind of conformer search, which is important, especially for larger, more flexible molecules. And then you select the level of theory. And then for each conformer, you need to optimize it, find the ground state geometry. And then for each geometry, you need to get the frequencies, because we are using harmonic approximation to get the ground state distribution. I will talk about that a bit more after. And once you have this, you sample the geometries from this distribution. Usually a couple hundred is enough to get a nice spectrum, so like 500. And then for each of this geometry, you calculate the excited states and transition dipole moments with TDDFT, for example, or something fancier. And then you get the photoabsorption cross-section. So it's not a super complicated workflow, but still it's a fair amount of work, and it's a bit annoying. It's not been really implemented that well. It's a bunch of scripts usually. And so we would like to make it a bit nicer, right? And so one reason why it's a bit difficult to make this easy is because quantum chemistry programs are not well known for their user-friendliness, let's say. So this is just an example of still a typical, interface. It's just a text file that you get, and you somehow need to parse it, and you need to get the outputs out and stuff like that. Of course, now that quantum chemistry actually can calculate stuff, we want to do more complicated workflows, and so people have been realizing that this is not enough. And there have been quite a few projects in recent years to kind of build a workflow manager that's kind of sitting on top and manages these calculations. So just very briefly to mention the overall architecture of ATMOSPEC. we are using AIDA as a workflow manager. AIDA is quite a known workflow manager in the material science community. And so it communicates with the quantum chemistry software, in our case, ORCA. It stores the results in the database and handles the overall workflow. Now, as a user, you don't really interact with this part. It's hidden because we are providing a graphical interface in the web browser. And this graphical interface, I'm using a library called AIDA Lab. So I will just mention as acknowledgement, I couldn't build this on my own. I've been using a lot of open source software. And so I would just like to acknowledge the people who built the original AIDA and AIDA Lab interfaces. Those are people from Switzerland. And I've been in very close collaboration with them. So just now to get to the actual point, how it looks. So this is roughly how it looks. You provide, in the first step, you need to generate the geometry. So you provide a smiles code and it will auto-generate the geometry for you. Then you need to select the level of theory. And then you press submit and you need to wait a bit because we are still doing up initial chemistry, right? And so it can be 10 minutes, it can be a bit more depending on the molecule. And then you get the spectrum at the end. So normally at this point, I would do a live demo to kind of show the program. That's allowed by the architecture because I could just connect through the web browser to our server in Bristol and I could launch the simulation in real time from here. I've chosen not to do that, just to be on a safer side, and I will present a screencast video to kind of, instead of static pictures, just showing how a typical workflow looks like. So this is the interface, and you can upload a file to get your molecule, or you can just generate it. In this case, we'll be generating glycolaldehyde. So this one has two conformers. One of them has a little hydrogen bond, as you see here. In the other one, the hydrogen bond is broken. You can see a Boltzmann population, of course, it's much lower for this, the other one. And then we get to the second step. We select the level of theory. We provide a reasonable default, but if you know what you're doing, you can change it, of course. You select the number of samples to 500, and then that's it, essentially. And now the simulation runs, and you wait a bit. Or skip over that part, and that's it. And you have a spectrum. So, and this is how it looks like. We can, in this case, compare to the experiment, which is the orange line, and we'll switch to nanometers, and we see that it's quite reasonable. We can see that the position of the peak is basically on top. We have some discrepancy in the intensity, and one thing that we can also look at is to decompose the spectrum onto different conformers. So in this case, we can see that the second conformer is actually redshifted towards the other one. So we the red line kind of shows the contribution of the second conformer, which is scaled by its small Boltzmann population in this case. And we also have a further analysis. So we actually implement the photolysis rate constant. So you need to provide a guess of the quantum yield. And this will then give you the photolysis rate constant. So which is what the atmospheric chemists are interested in. I think that's largely it. Now, of course, there are the results. The accuracy of the results will depend on the system and on the type of excitation. And there are essentially this kind of workflow is quite general. So I've been talking about application in atmospheric chemistry and UV spectroscopy, but we've been using the very similar workflow for other spectroscopies as well, and finding it that it works quite well. So for example, in this case, we were looking at photoelectron spectroscopy. We can look at X-ray absorption spectroscopy and many other kinds of spectroscopy. So if you're interested and have a use case that you think might be interesting, you come talk to me after. Now, there are three kinds of errors that you can get. One is coming from electronic structure. That's always going to be the case. TDFT is beautiful, but sometimes it fails, especially for like radical molecules and more challenging electronic structure. The other error is coming from the nuclear ensemble approach itself. This is what I discussed. And then the third error comes from the how do we sample the ground state geometries? And I'm going to quickly mention a bit about that part. But just to get back to the original kind of equation and original goal, we've now got a way how to calculate the absorption cross-section. Now the question is, could we also calculate the quantum yield? I will be showing some results for this particular molecule, metal peroxide, which we've done together with Antonio Pereira, who was a postdoc at the time, but now he's in Zagreb on his own position. And so to answer my own question, yes, we can do it, but it takes a lot of work. So you need to actually do the dynamics. So you need to have an electronic structure method that can describe the excited states, and you need to actually run the dynamics, which is tricky. I'm not going to talk much about it. There are people who will talk about it today and tomorrow, but we can do it. And the results in this case were quite nice, and we can compare to the experimental data which we have for this molecule. And not only we get the quantum yield, but we also get the wavelength dependent quantum yield. So the quantum yield actually depends on the energy that you put into the molecule in this case. So in this case, you can either dissociate a hydrogen or dissociate an OH. And depending on how much energy you put in, this yield will change. And now there are some technical subtleties that you need to be aware when doing this, because otherwise you can get quite different results. And so one subtlety that I want to discuss, and that's connected to the spectra, is how do you sample the initial conditions for the non-adiabatic dynamics. So there are many different methods for non-adiabatic dynamics, but the ones that we are interested in and that are applicable for larger molecules are often based on classical trajectories. And you somehow need to initiate those classical trajectories. You need to provide initial position of the atom and initial momentum, right? And so how do you do that? One way that in the photochemical community people would tell you that they do is called Wigner sampling. That sounds very fancy, but don't be fooled, because Wigner sampling usually just means harmonic approximation and sampling the harmonic normal modes of the molecule. That's it. And of course, harmonic approximation is nice, but the molecules are often not harmonic. And in this particular case, we have this hydrogen over here that can essentially rotate freely along the dihedral angle, and we have this double well potential with a very low activation, the very low barrier. And so if we look at the kind of exact results from sampling the geometry in the ground state, we get a very smeared distribution. But if you do the Wigner sampling, just you pretend that this is parabola here, then obviously you will get something that's quite different. And so this is a problem on its own, and this is very typical for these low frequency and flexible molecules. In this case, there is an additional problem that comes from the fact that we are sampling these normal modes in Cartesian coordinates. And the fact that we are not able to sample the dihedral correctly also, unfortunately, influences the oxygen-oxygen bond lengths, which are normally, we would think those are quite harmonic. It's a strong covalent bond. But because we are sampling in a Cartesian coordinates, instead of hydrogen rotating like this, it will kind of do this motion. And I can show you with my hand, but this motion actually stretches the oxygen-oxygen distance. And you can see that the distribution here is shifted by quite a lot. And this, you can look at this as a correlation plot where this is kind of the exact results, and this is what you get from Wigner, and you can see this weird shape. And well, the result of this is quite disastrous in this case, because this is what you get as a UV spectrum. So this is the dashed line is the experiment, and this is what you get from the Wigner sampling, which is very, very bad. And in turn, what this means is, if you look back at the plot of the wavelength-dependent quantum yield, if you just did the Wigner sampling, which most of the people are doing, you would actually get these red points, and essentially the quantum yield is constant over the wavelength. So completely qualitatively wrong results. So this is just to say that one needs to be quite careful about this. Now the question is, can we do something better, right? And just very briefly, we can. There is a method called quantum thermostat. I'm not going to go into much of a detail, but essentially the idea is we somehow need to sample the full potential, full anharmonic potential. And one can do that with ab initio MD, ab initio dynamics. But you cannot do classical MD, because if you do classical, the distribution will be way too narrow, and your spectra will be completely wrong. So you need to include the zero-point energy. You need to include nuclear quantum effects. One way to do it is with path integrals, and that's quite established method, but it's expensive, and also normally it will not give you the momentum. So you cannot initialize your semi-classical dynamics with path integrals. There's another kind of more approximate method called quantum thermostat, which essentially runs classical MD, but it heats up your system and it puts more energy into the modes and you essentially put so much energy that you broaden your distribution until it matches the quantum one. So in the classical case, for harmonic oscillator, you have a Gaussian distribution. That's just a Boltzmann distribution, right? And if you solve this quantum mechanically, you actually get also Gaussian, but it will be wider, right? Because you are including the zero-point energy. And you can imagine that at certain temperature, if you increase the temperature of this distribution, at some point, you will reach a temperature where you will exactly match this one. And so this magical temperature you can derive. And the only problem is that this temperature depends on the omega, so on the frequency of the normal mode. So you somehow need to make your system non-equilibrium, and you need to pump in energy into high frequency normal modes and keep the low frequency normal modes at lower temperature. So quantum thermostat is a non-equilibrium method which enforces this condition essentially. And it works very, very well. If I went back, I could, some of the distribution that I showed actually showed the comparison between full path integral and quantum thermostat, and it works very, very nicely, even for the anharmonic systems. So this is what you can use. We have a program that implements this. And so this you can use for both initializing the semi-classical MD, but you can also do that for the UV spectrum. So we're currently not have that implemented in ATMOSPEC, but if you really need a high accuracy spectrum, this is what you would do. Okay, that's it. I would like to acknowledge the group again. Thank you, thank the funding agencies, and thank you for your attention.
Thank you. Thank you, Daniel, for the very nice talk. And we already have a question.
Ahoy, Daniel.
Hi.
Very nice presentation. So I have many questions, but I'll reduce myself to something. So I was wondering, so you can of course afford doing the nuclear ensemble method because you have very small volatile molecules. And probably it can be expanded to other systems, but my question is, have you thought about simulating the spectrum in a different way? For example, using this vertical gradient approach just by doing, you know, harmonic frequency calculations in the ground state and then getting your line broadenings from elsewhere? And if yes, would it give you comparable results to the nuclear ensemble method?
it would very much depend on the molecule. Generally, it would be, well, if you have a molecule that's bound harmonically on the excited state, then you can get reasonable results with that. But it's not generally applicable. And the whole kind of idea of this is that the workflow is applicable for large number of molecules, and you don't really need to, think about it or tweak your results. The approach that you're mentioning, if you hit a dissociative state, then it will be completely wrong. And also, the thing that I mentioned about non-condon effects is crucial, because if you just do a vertical excitation and you have a weakly allowed transition, because, for example, the molecule is symmetric, then the spectrum that you get will be very weak. But if you actually do the full sampling, it turns out that once you break the symmetry, the transition dipole moment can be much, much larger. And so the nuclear ensemble approach is crucial to get these weakly allowed transitions, which are quite common, for example, in carbonyl bonds. That's the unpi star transitions. That's absolutely critical. So, yeah.
Thanks.
There is one question in the back also.
So pretty good. So pretty great presentations here. So I'm not quite sure if you already mentioned this somehow, but in terms of accuracy, how far do you think you can go until the whole system, basically, until the whole simulation just started to break down and just diverge from what it was supposed to be theoretically?
Yeah. So as I mentioned, there are several things that we are approximating, and it very much depends on the molecule which of these three things is getting crucial. So, for example, for the metal peroxide, the harmonic approximation that we're doing is the thing that's killing us, right? Or can kill you unless you're careful. For other molecules like the Kriege intermediate, for example, which is a radical, the electronic structure is difficult. So if you try to use TDDFT, no way, it will be completely off. So you always need to be careful about the electronic structure, and we're now actually have a project on benchmarking the various method against CC3, which is accurate and can give you a reference data. And so it's hard to say, I guess, to answer your question. It depends.
Okay, so maybe it's better to when it comes to dealing with this kind of program to have, let's say, reference data.
Yeah. So one question one thing that we are planning to do is essentially, we cannot guarantee accuracy, but we would like to detect where we think you're entering the dangerous territory. So, for example, we can detect that you have a radical or you have some difficult electronic structure, and we can give you a warning, for example. So we would like to do these kind of things where we can essentially give you a warning that you need to be careful and maybe consult an expert or something like that.
All right, thank you.
The last question.
Hi, Daniel. Nice talk. So, do you have any plan to include the photo emission? Because as I understand, you are working with nuclear ensemble, and the workflow will be pretty similar, right?
Yeah, currently we don't have a use case for that, but if you're interested, then I think it would be reasonably easy to implement. The only problem is that for photo emission you need to optimize the excited state, and that's tricky.
Yes.
So I think now many programs actually can optimize, like using TDDFT can do it.
Of course.
So I think it should be possible, a bit more tricky.
Yes. And I have a comment to Rafael's question. So for the vertical approximation, maybe you are losing a little bit more, because with the nuclear ensemble approach, there is the advantage that you are deforming the molecules, and by that you are effectively including some of the oscillator strength to your molecule. So that is why it deliver most of the cases good results than the vertical approximation. Of course.
But I mean, you don't really, you can go quite large.
Yes.
Because as long as you restricted yourself for TDDFT, then anything that's able to be in gas phase you can do. And we are planning to implement interface to TeraChem which runs on GPUs, and then you can calculate almost anything with TDDFT that's relevant. So I don't think that's really the computational cost. There are ways that we can bring that down. Yeah.
Let's thank Daniel again.